Alright, welcome everyone to today's video. We're going to start talking about molecular orbital theory and applying it to Huckel MO theory. So in this video we're just going to first introduce kind of molecular orbital theory and some basic ideas with pi conjugated systems and molecular orbital theory with them. Okay. So when looking at MO theory for conjugated molecules, and specifically focusing on the pi space, right? Right, those pi spaces are composed of p orbitals, right? And the p orbitals, right, can have, right, if you have a p orbital, right, you have a plus and a minus section to it, right? Place where the wave function is positive, place where the wave function is negative, right? And right, and so you can have those things match up, right? Plus or minus, and then you have like a pi bonding orbital, where you could have, right, plus minus, minus plus, right? Really poorly drawn, right? But an anti-bonding orbital, right? Pi and a pi star orbital type thing, right? And so, right, when you get to more and more conjugated systems, right, you can construct the pi molecular orbitals by just looking at this type of thing, right? That whether or not these orbitals are, say, all up or mixture of up and down, things like that. So what's plotted here actually is kind of giving us, you know, some insight into, right? You have two ethenes, right? And then you can form butadiene, okay? Well, if you were to start with two ethenes to form the butadiene, right, these two ethenes you have, for a given ethene, right, you have the pi bonding orbital and the pi anti-bonding orbital, right? Pi bonding, pi anti-bonding, okay? And I have two of those orbitals, right? So for two ethenes, right, I can, right, and each ethene has two electrons in the pi space, right? So I just have the two electrons occupying the pi bonding orbital, right? Now, if I form butadiene, right, what I can do is I can take these two, right, I can think of butadiene as taking two ethenes here, where I have two pi bonding orbitals, and I can add them together, right, to get the bottom curve, or I can subtract them to get this upper curve, right? The bottom curve, add them all together, so everything's completely conjugated, right? This upper curve, I kind of subtract them, so I get same phases here and some phases here, right? Similarly, I can do the same thing with the anti-bonding orbitals, right, where I can add them, which ends up being those orbitals, or subtract them, which ends up being those, okay? Based on how they're drawn here, okay? And here I have then kind of bonding across these guys. Then here I have no real bonding across any set of atoms, right? And so if you notice this orbital energy diagram, if you kind of look at this and you see, okay, in this very bottom diagram, there's no nodes. There's no place where there's not a bonding between the p orbitals, right? In this, or in the second energy diagram, there is a node, right? It's located right there in that dashed line, right? And then in the third orbital, there's two nodes, right? And then in the fourth orbital, there's three nodes, okay? Right, and basically there's a node wherever your wave function changes sign, right? It goes from red to blue, to red to blue, say in the very top kind of psi 4 here, right? And so there's a very simple way to at least roughly organize the energies of your pi orbitals, and it's just this idea: the more nodes you have, the higher energy your orbitals are. We've talked about this when we talked about particle in a box and things like that, right? Because the more nodes you have, the larger curvature your wave function has to be, right? Because if you have a bunch of nodes, right, if this is, say, x equals 0, right, or whatever, y equals 0, sorry, not x, but y equals 0, right? Okay, the x-axis, right? If you have a bunch of nodes, your wave function's got to go up and down, right, across that axis quite a bit, because each time you have a node, right, it's got to cross the axis, okay? Well, to do that, there's got to be a lot of curvature, right? Your wave function's got to be turning over a lot, and there's got to be a lot of curvature. So this wave function has a lot of kinetic energy in it, right? And so the more nodes you have, the more kinetic energy that wave function has, right? The higher its energy is going to be. Okay, so we can look at benzene. Okay. Right, and even in benzene, even if it's not as easy to see as butadiene, right, you can still count the number of nodes, right? In this bottom orbital, right, there's no nodes, things completely bonded all around, okay? And the next set of orbitals, you have one node between those carbons and one node between those carbons, right? Similarly, you have one node here, one node over here, right? Then up here, right, you end up having 1, 2, 3, 4 nodes here. Okay. Here you have 1, 2, 3, 4 nodes. Okay. And then the top orbital here has 6. Right. 1, 2, 3, 4, 5, 6. Right. There's a node between each carbon neighbor. Right. And so we go from number of nodes is equal to 0 to 2 to 4 to 6. Right. So they're still organized by energies. Right. Now drawing these orbitals from I. Right. Butadiene, right, like these, linearly conjugated, like, alkenes, right? I could draw, if I wanted to, what the pi orbital space looked like for all the different potential, pi bonding and anti-bonding type orbitals and things like that, right? It's fairly easy to try to do that. For benzene, though, it's not as obvious when there's rings and things, just because there are some orbitals that exist where there's actually no contribution from some atoms, right? So, right, in say this molecular orbital here that I've circled, okay, right, carbons on the ends here, the carbon on the left end, the carbon on the right end, right, they don't contribute to the pi orbital space, right? And it's not obvious to think, oh, that will be a molecular orbital, right, off the top of our head, okay? And so this is where things like Huckel-MO theory would come into play to be able to predict what these molecular orbitals look like, okay? And we'll talk more about that in the next video, okay? But we're going to finish up this video with just a couple of questions related with what we talked about in this video, as well as just recapping some just molecular orbital theory from previous lectures. So the first question here, which molecule has the highest first ionization energy? Okay, so the first ionization energy, that's the ionization potential, right? So what we're going to look at is we're going to look at the MO diagrams for all of these molecules, okay? Okay, so we got C2, N2 is going to look the same type of MO diagram. N2, NO is going to have the same type of diagram. Oops. NO, and O2 is going to have, that could be kind of switched to O2, right? So C2, I have a total of 1, 2, 3, 4 valence electrons, so 8, 1, 2, 3, 4, 6, 7, 8. Okay. N2, I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And O, I got 1, 2, 3, 4, 5, 6, 7, 8, 10, 11. Okay. And O2, I got 1, 2, 3, 4, 5, 6, 9, 10, 11, 12. Okay. So these are the molecular orbital diagrams for these 4 different diatomic molecules, right? And so the one that has the highest ionization energy, right, is the one that is the most difficult to remove an electron from, right? Right. whichever one it requires the most amount of energy to remove an electron, okay? And so for that, right, it's just going to basically, right, these molecular orbital diagrams, right, are drawn such that energy is increasing as you go up, right? So for C2, I got to remove an electron, right, from the lower energy orbital, okay? And so that orbital is going to be at a lower energy than any of the other ones, so it's going to be C2 here, okay? Right, so which molecule has a bond order which is different from the others, okay? So here I'm just going to first count the number of electrons because it might be kind of obvious from there. So NO, right, we kind of did that in the last one. NO has a total of 11 electrons that I got to fill in, okay? O2 plus is also going to have 11 electrons. N2 2 plus is going to have N2 has 10, so it's going to have 8 electrons, and then CO minus is going to have 11 electrons, okay? So just looking at the different number of valence electrons, it's going to be C here, right? You could draw the MO diagrams and see that C will be, in fact, different, okay? But just counting the number of electrons gave us the answer, right? Now you can have a different number of electrons and have the same bond order, right? Right, I could have something as simple as this is Li2, right? And compare that with B2. Okay, these both have a bond order of 1, so right, it does, just because they have a different number of electrons doesn't mean they can't have the same bond order. But in this case, 11 versus 8, they will have a different bond order, so it's going to be C. And then finally here, right, I have a diagram for the pi orbitals for trans-butadiene, okay? Right, the shading is trying to indicate whether it's a plus or minus sign. And so the question is, which molecular orbital is the lowest unoccupied orbital for this system, okay? Right, and this is what trans-butadiene, right, looks like in terms of Lewis dot structure, right? So basically, these 4 orbitals all have a different number of nodes, right? They've been highlighted here. This is 0 nodes, this is 2, this is 1, and this has 3, right? And so if I organize this in terms of energy, this is going to be D, this is going to be C, this is going to be B, and this is going to be A, right? And so trans-butadiene has 4 carbon atoms. Each carbon atom will contribute 1 pi electron. So I have a total of 4 electrons to fill. So I've occupied my D and C orbitals, and my B is the lowest energy unoccupied orbital. So the answer here is B. Okay. So that's just kind of a recap of MO theory as well as applying it a little bit to pi systems. And next we're going to start talking about Huckel MO theory in the next video.